Welcome to several examples on how to write the form of a particular solution to a linear second-order non-homogeneous differential equation. The reason we want to know how to do this is because in order to apply the method of undetermined coefficients, we do have to guess the form of a particular solution, which we'll call big Y sub p of x, in order to find the general solution to the differential equation. So let's take a look at our examples. Again, our goal here is to write the form of the particular solution, which we'll call big Y sub p of x. Notice we do have a linear second-order non-homogeneous differential equation where the right side of the equation, often referred to as g of x, involves both the sine function and the cosine function. So we're looking for a function big Y sub p, where if we substituted in the function, its first derivative and second derivative, we'd end up with this function here on the right. So for the form of big Y sub p, we'll consider one term at a time. Let's start by considering 2 sine 3x. Well, it's probably safe to assume it's going to include an undetermined coefficient times sine 3x, so we'll start with that. So we have a sine 3x. But notice how the derivative of this term would also involve cosine 3x. So we also have to include an undetermined coefficient times cosine 3x. So plus b cosine 3x. So just considering the first term, this would be the correct form for the first part of the particular solution. But now we also have to consider the second term of plus 4 cosine 3x. So again, it's going to be safe to assume that we'd have a constant times the cosine function, or cosine 3x. So let's call it c times cosine 3x. But now the derivative of cosine also involves sine, so we'll also need plus d sine 3x. So these two terms would be from the second term involving the cosine function. But notice how there is some repetition here, so we can shorten this function. Notice how we have two cosine functions and also two sine functions with the same angle. Notice how all the angles are 3x. If they weren't the same, we wouldn't be able to shorten this. So let's write this as big Y sub p of x equals, let's factor out sine 3x, leaving us with a plus d sine 3x. And then we'd have plus quantity b plus c times cosine 3x. Well, notice that a plus d is just another constant, and so is b plus c. So let's go ahead and write this as big Y sub p of x equals, we left off with d, so let's say e sine 3x plus f cosine 3x. This would be the form of the particular solution for the given differential equation. Let's take a look at another example. Looking at the right side of the equation, notice how we have 2x squared, and then we have minus 3 sine 5x plus 1. So if we wanted to, we could rewrite the right side of this equation as 2x squared plus 1. So this would be a quadratic function minus 3 sine 5x. So we can think of this as a quadratic function and then minus a sine function, which means for big Y sub p of x, our particular solution, it would take the form of a quadratic function with undetermined coefficients, which would be ax squared. We still have to include an x term, so plus bx plus c. And then for the sine function, we could have plus d times sine 5x. But again, because we're also working with derivatives, and the derivative of sine involves cosine, we would have to have plus e cosine 5x. There's no repetition here, so this would be the form of our particular solution. Let's take a look at one more in this video. Notice in this example, it says to assume there are no terms in y sub p, our particular solution, that are duplicates in little y sub c, which is the complementary function, or the first two terms of the general solution to the non-homogeneous differential equation. This is important because if there was duplication, it would affect our approach to forming the particular solution. We'll take a look at this case in the next video. But for this example, because there's no repetition, we can go ahead and set up big Y sub p. So notice how the first term is 4e to the power of 2x. So for the particular solution, we'd start with a times e to the power of 2x. Remember, a is some unknown coefficient. Looking at the second term, we have minus 3x times e to the power of negative x. We need to think of this as a linear function times an exponential function. So for a linear function with unknown coefficients, we would have to have plus the quantity bx plus c times the exponential. And then we'd have plus d, an unknown coefficient, times the exponential e raised to the power of negative x. But in this case, I think we can simplify this. Notice if we distribute here, we actually would have 2 e to the power of negative x terms. Let's go ahead and show that. Big Y sub p of x is equal to a e to the power of 2x, and then we'd have plus b x e to the power of negative x plus c e to the negative x, and then plus d e to the negative x. Notice how these are like terms, so we could write this if we wanted to as a e to the 2x plus bx e to the negative x plus quantity c plus d e to the power of negative x. Well, c plus d is just a constant, so we don't need both of these. We'll go ahead and say big Y sub p of x is equal to a e to the 2x plus bx e to the negative x. Let's go ahead and just use c again, because we didn't need this term here. So plus c e to the negative x. This would be the form of the particular solution to the given differential equation. And again, this is important because if we were going to use the method of undetermined coefficients, we would use this as the function that we're guessing would be a particular solution. I hope you found this explanation helpful.